This is the Geometry Unit 6 Lesson 5 video over kites and trapezoids. I'm going to start with a kind of overview of the different characteristics of kites and trapezoids, and then we'll work through some proofs, and then we'll look down at the lesson questions, and I think you'll see it's mostly vocabulary, but I'm going to jump into the characteristics of kites and trapezoids. All right. I can get this to load. Here we go. All right. First things first. Trapezoids. A trapezoid is a type of quadrilateral. And if you look back at the sort of family tree that we looked at, or that I put in the notes previously, you'll notice a trapezoid does not fall under the category of parallelograms. It is its own sort of branch of the family, so to speak. That is because trapezoids have just one pair of congruent sides. So, this other way, back here. There we go. All right. Trapezoids have just one pair of parallel sides. And when we say that, we mean just these two, what we call the bases, are parallel to each other. So the two sides in a trapezoid that are parallel are called the bases. And then the other sides that are not parallel to each other are called the legs. So trapezoids can come in sort of all sorts of different arrangements in terms of the way that these legs are oriented. So, for instance, you could have a trapezoid with like something like this. Sorry about that. It's not a very straight line, but that's okay. You could have it with a really, really long kind of leg stretching out that way. You could have them with just barely kicked out like that. You could have it with one side kind of going like that, and the other having a right angle. So trapezoids, really, the real main characteristic that has to be true in all of these cases is that these two sides are parallel. And then the orientation of the other legs is sort of open. So it could be a lot of different things. You can see I've got a few different types here. And the key terminology you need there is just that these parallel sides are called the bases, and then the legs are these other sides that are not parallel to each other. So that's the main idea about trapezoids. That's the kind of defining characteristic. And then we have what we call, the rest of this is all about a unique type of trapezoid called an isosceles trapezoid. And that word isosceles, we've heard in geometry before. When we talked about isosceles triangles, we talked about triangles that had two sides that were the same, and then some other side that was not the same length. So isosceles trapezoids have the same idea. They have two legs that are actually the same length. So as opposed to some of this other example up here where the legs are different, in an isosceles trapezoid, the legs have the same length. And that's the first main characteristic of isosceles trapezoids, is that the legs are congruent to each other. But there's actually more that comes out as you look at these closer. For instance, if you look at the base angles, which would be these pairs of angles here, and then also the pair of angles up here, you'll see that they are congruent. So the pair of angles on this bottom base is congruent, and the pair of angles on the base up top is also congruent. So the orange and the green there are congruent to each other. So base angle pairs are congruent. Not only that, if I take one of the green angles and one of the orange angles and I add them up, they add up to 180 degrees, also known as supplementary. So these pairs of angles on the side, here and here, are supplementary. Again, remember that means that they add up to 180 degrees. All right. And then lastly, if I draw in the diagonals of this isosceles trapezoid, they are congruent to each other. Now, they don't bisect each other or anything like that, like we were doing in some of our other figures, but they are the same length. And so these are kind of the big characteristics of isosceles trapezoids. Okay, so that's kind of everything you need to know about trapezoids, with one exception, which we'll get to near the end. But let's jump over to kites. I'm actually going to be focusing on the bottom of this diagram here, not the stuff about trapezoid midsegment. I'm actually going to cover that up for now so we don't really get too distracted by it. But kites. So kites are another type of quadrilateral. So just to jump back really briefly, if we look at our family tree, we see that we have our parallelograms in the middle, which we've covered in the first few lessons here. Then we just talked about trapezoids and isosceles trapezoids. And now we're talking about kites. So kites are yet another branch of this family, and they have no parallel sides. More than that, they do have one kind of special thing about them that we need to be aware of, and that is that kites have two pairs of consecutive sides. So just to kind of like point that out, that would be talking about this side and this side on the diagram. This side and this side are congruent to each other. And then this side and this side are congruent to each other. So we have this dark blue and this turquoise are the two pairs of consecutive congruent sides. Remember, consecutive means they're next to each other. So that's what we're talking about when we say that. So that is the defining characteristic of a kite. They have these two pairs of consecutive congruent sides. Additionally, the angles that are on either side right here are congruent to each other. So this angle and this angle are congruent, not the angles on the top and bottom here. Those are not congruent, but the angles on the side are. We call those the non-vertex angles because we call these two corners, each of them are a vertex. And then these non-vertex angles here and here are the ones that are congruent to each other. So that's the next kind of major characteristic there. Next, it says the diagonals are perpendicular, which is actually going to be over here on this diagram right here. So when we look at this one, I've drawn in the diagonals. And the things that we need to know about that is, first of all, the diagonals are perpendicular to each other. They form a right angle. If you've ever made a kite like this, you know that one of the things you do is you put two sticks together in a perpendicular shape in order to provide kind of the best support for this kite shape, which is kind of the concept here. These lines are perpendicular to each other, as indicated by this little box right here. Remember, perpendicular means they form a 90-degree angle. Lastly, there are kind of two things that happen with this diagonal that runs on the longest part of this shape. So this diagonal right here does some things in this figure. Let me try to get that line drawn out as straight as I can. There we go. It bisects the entire figure. You can probably tell just looking at this that this is cutting this shape in half. And either side of that line, they are congruent things. There is a congruent angle here and here. There's another congruent angle to each other, pair of angles here, and then there are congruent line segments here because this is bisecting that figure. It's cutting it in half. So things that are opposite of that line are going to be congruent to each other. So those are kind of the main characteristics of kites and trapezoids. So let's jump over to the lesson, and I'm going to do what I've done in the previous lessons, and we're going to go over the proofs. I've just gone over all the material up there. All right, they start us off with kites. First thing they say, MNOP is a kite. Okay, that's our given. So we have our statement and our given for that first thing. And then it says it wants us to prove that N is congruent to P. So we're looking at those angles right there. Now, we know that that is a characteristic of kites, but we're going to show how we know that. How can we prove that? And it's going to be a lot of the same processes we've been using in some of the other lessons. So let's take a look. MN is congruent to MP. That's this one and this one. They're marked on the diagram. Oops. Sorry about that. MN and MP are congruent to each other. Sorry, let me fix this. Got a little bit of error there. Okay, there we go. MP and MN are congruent to each other. And PO and NO are congruent to one another. Okay, so we see that. How do we know that? Well, that's the definition of a kite. And the way we can know that is that statement 1 is giving us the only information we have, and so it has to be providing the answer to number 2. So it's the definition of a kite, which is answer choice F. Sorry about that. That's the answer choice F. So let's go up here and say, because it's the definition of a kite. All right. Next one, MO is congruent to MO. If you've been watching these videos, you know that that has to be the reflexive property. So let's look down here. Answer choice D is the reflexive property. So we go answer choice D. Anytime you have the same thing congruent to itself, you're dealing with the reflexive property. Next one. Okay. We're not really sure. We don't know either. Now, they're giving us a bit of a challenge here. They're kind of making us do more and more of these proofs. Well, I'll tell you something I know. I know that based on the way this diagram is drawn, it's clear to me that they are going to try to do something about these two triangles. And so let's look for something about triangles. And I see in answer choice H that they are going to prove that MNO and MPO, which are the two triangles I've outlined here, are congruent. And we could have also known that by looking up here and seeing that we've proven a pair of congruent sides, another pair of congruent sides, and a last pair of congruent sides, 3 of them. And when we do that, we know that we are looking at the side congruence relationship. So we're going to use this one right here. So we go up here and we choose side, which is A. And then if you've been paying attention to the videos, you know that after we prove that a triangle is congruent, the next thing is always C, P, C, T, C. Because if those two triangles are congruent, then that means that all the different parts of that triangle are congruent. And so that's going to be answer choice B. All right. So hopefully that makes sense to you. Thank you for watching this and kind of at least following along. This material here is all the properties we already went over. So we're going to just go all the way down here. And we're going to get to our proof about this trapezoid. So it says here ABCD is an isosceles trapezoid. Okay, we need to know that. And then we need to prove that AC is congruent to BD. All right. Well, we know that already because we learned that in my little lecture previously that these are congruent. So let's get this blue still popping up every time. Let's just clear everything. All right. The first thing it says is AB is congruent to CD. And again, if you start with information about isosceles trapezoid, you should be pretty confident that that first response is going to be the definition of that thing. So let's go look. And there it is. Answer choice E, isosceles trapezoid. So that has to be answer choice E. Then it says AD is congruent to AD. Seeing a trend here. If we ever have something where it says this thing is congruent to itself, that is the reflexive property. Let's go look. Reflexive property is answer choice H. Very common. There we go. So we know it has to be that because it's the same thing congruent to itself. Then we get an angle. BAD is congruent to CDA. Okay. How could we know that? Let's look at where those are. BDA is congruent to CDA. Well, I did that backwards. I'm sorry. BAD, read more carefully, BAD is congruent to CDA. Well, how do we know that? Well, let's look at our different properties down here. We have some triangle stuff, PCPT, I don't know what that is, CPC, transitive property, and there we go. Look, isosceles trapezoids have congruent base angles. That is a property that we learned. I just showed you that. So that's where that is coming from, because these are the two base angles. And so in isosceles trapezoids, that has to be congruent. So let's go see, that was number G, or letter G. There we go. All right, look at this, side angle side. That means we're dealing with some kind of triangle congruence situation. Remember, SSS, SAS, ASA, and AAS always are going to be the reasons for congruent triangles. So let's go look, and we have two options. We have BAD is congruent to CDA, and BAC is congruent to CDA. Let's go up and look. You probably guess this should be a big hint right here. The fact that that angle was the last statement should tell me something really clear about the triangle that I'm trying to prove. But let's go look. BAD, erase all this. BAD is congruent to CDA. That looks pretty good to me. Those were the angles from this previous one, so let's choose answer choice A. And then lastly, we know what happens after we prove triangles. The next thing is always CP, CTC. Answer choice C. All right. Make sure you get those answers down. Feel free to rewind and go back. Let's jump down and see what else we have here. Okay. 3, 4, 5, all the way down to number 16. All of those are vocabulary. So make sure that you are utilizing the vocabulary information there and answering those questions. And then I'm going to walk us through trapezoid problem number 17. There is one other property of trapezoids that we didn't go over. I said I skipped it and we'll come back to it later. And it's what's on the top half of this notes page. On this notes page, it says trapezoid midsegment. So a trapezoid midsegment is the line connecting the midpoints of the two sides. So if M is the midpoint of this side and N is the midpoint of this side, then the thing connecting them right here, let's do a different color here. This is what we call the triangle midsegment. All right, so what do we know about that? Well, the two main things you know about the midsegment is that, first of all, it's also parallel to these sides. So if those are parallel, that's parallel as well. That's the first thing you know. Then the other thing you know is this. the midsegment is half the sum of the bases. So that means that if this is 11, like you see there, and this is 19, like you see there, then I can add up those numbers like you see here. I can do, since it's half the sum of the bases, I can do 11 plus 19 divided by 2, and that gives me 30 divided by 2, which is 15 centimeters in this example. So that's how you do trapezoid midsegments. The pack is going to take it a lot easier. It looks confusing, but it's actually not. They're going to actually calculate the values of these lengths and then use a formula to find that. So I'm going to walk us through this one. And just give me a second. I'm going to pause this video. Okay, looking at number 17. We're going to walk through this, I think, because this is a little bit of a strange way to do this. But what they're going to have us do is they're going to have us find the value of the distance between A and D, the distance between B and C, and then do the formula to find the distance between E and F. They make it way overly complicated. So let's talk through this in a little bit simpler terms. They're using a formula to find the distance between A and D. But let's just take a step back and use common sense. This distance starts at 0, goes to 8. 1, 2, 3, 4, 5, 6, 7, 8. That distance is 8. There it is. That's all we have to do. Let's go up here. This goes from 2 to 3, 4, 5, 6. See, it goes from 2 to 6. That's a distance of 4. Again, they make it more complicated than it needs to be. EF. Well, I don't need to calculate the distance of EF. I should know what it is, but let's count it anyway. EF goes from, goes from 1 to 7. That's 1, 2, 3, 4, 5, 6 units. 6. Then they give us the actual formula we talked about in my lesson, which is that 1/2 of the sum of the bases. So 1/2 of 8 plus 4, and that's coming from here. We're taking the answer to this, 8, and we're putting it here. Taking the answer from this, and we're putting it here. AD and EF, or sorry, AD and B, not EF, AD and BC. We're taking these, and we're putting it here and here. What does it equal? Well, we already know the answer. It equals 6, because 8 plus 4 is 12, divided by 2 is 6. Does EF equal 1/2 of AD plus BC? Of course it does. We know that because this is an isosceles trapezoid. So the answer is yes. So I've walked you through that one. You'll see some more like it on the quiz, but make sure you do the vocabulary on this. I think the quiz and the test here are pretty vocabulary heavy. So make sure you're spending time maybe writing down lists of the ones that are, especially the ones you notice are repeated on the quiz. And that is the end of lesson 5.